Let's look at some solving or finding definite integrals and also other applications of integration of antiderivatives. So these are kind of special, unique type problems where we're dealing with absolute value, finding definite integrals involving absolute value. We could apply using separating them out as individual functions and going through piecewise functions and doing power rule. But I think it's easier if we just draw this graph out and just treat it like areas, adding areas of two triangles together. So as a reminder, area of a triangle is 1/2 base times height. And first thing we can do is just try to sketch this graph out. So y equals absolute value of x plus 1. That's going to be absolute value functions have a V-shaped graph, either right side up or upside down. The plus 1, it just means that it's going to take a vertex that was initially at 0, 0 and shift it left 1 unit. So that's my vertex. I'm going to extend the graph vertically or upwards because this is a positive absolute value function, so it's going to be a V right side up. And it's going to stop at -3 and at 2, and that's where the heights of my triangles are going to close off. And if we just treat this like right triangles that we can find the count to find the base and the height, we know that this is units, 2 units there. If I plug -3 in for the x, I get -3 plus 1, which is -2. Absolute value of -2 is +2. So height of 2, width of 2, so 1/2, 2 times 2, that's going to be just 2, or 4/2. And here, my width is 3, my height is 3, so 1/2 base times height, we get 9/2. So 4/2 plus 9/2, we get 13/2. For 14, we're asked to find the derivative of a definite integral. So whenever we see these two operations paired on top of one another, applying to the same expression, we can go through the second theorem, which essentially is just going to tell us that these are going to cancel each other out. This expression is largely going to remain unchanged. But what does happen is through this process, that upper bound variable does end up plugged into the expression, and then the upper bound's derivative does get applied. So it takes the form of f of p of x times p prime. So if we think of it that way, then we can plug the t in for the x. We get square root of t cubed plus 1 multiplied by t's derivative. T's derivative is 1 because that's a variable to the first power. And that just cleans up to be square root of t cubed plus 1. 15, same idea. Apply second theorem because we're pairing derivative on top of the integral. But we don't have to worry about anything that is a constant. Anything that's a constant is just going to wash out, is not going to have an impact on our final answer. Just the bound that has a variable in it. So again, the upper bound gets plugged into the expression, and then we multiply it by the upper bound's derivative. So the upper bound, when it gets plugged in for the variable, it becomes sine of quantity x squared. That's here. Multiplied by x squared's derivative, which is 2x, which is here. And then we clean this up to make it 2x squared of sine of x squared. Answer choice E. Okay, number 16. This is going to be, if we look at this problem here, can't expand too complex for one rule to handle. So we look at u substitution. Okay? So maybe what if our u value is what's in the exponent? That x squared's derivative is going to produce 2x, and that x is going to cancel out with that x, so it looks like this will be a good fit for u substitution. We let our u value be x squared. Derivative is 2x. dx equals du over 2x. We make our substitution. The exponent gets replaced with u. dx gets replaced with du over 2x. X is canceled out. We push the 1/2 out in front. We have integral is e to the u. Antiderivative is e to the u. Now, we don't want to stop here and use the bounds of 0 and 1 because these are in terms of x, but that's in terms of u. So what we want to do next is we want to bring that u back in terms of x, replace the u as x squared. Now we can work in those bounds, the 1 and the 0. Okay? The 1 plugs in for the x, and for the x squared, and the 0 gets plugged in for the x squared. So two big common mistakes. One is not going far enough to match the variable with the bounds. And the second mistake that I see a lot is thinking that every 0 as a bound is going to wipe everything out. It's going to turn everything to be 0. But that's not always the case. It occurs sometimes, but not every time, especially if we're plugging into something that is an exponent. So e to the 0 doesn't become 0. E to the 0 becomes 1, and 1 times 1/2 is 1/2. So 1/2 e minus 1/2 times 1. We can factor that out as 1/2 parentheses e minus 1 to make it match answer choice B. All right, last page here. This is number 17. All right, so 17. We have cosine squared theta, sine theta. This is not going to be something that we can expand, so we want to look for u substitution. It's a lot easier to find an appropriate u value if we can get some parentheses to show up. So I'll rewrite the cosine squared as cosine parentheses squared. So once we see the parentheses, that's a good indication that whatever is inside the parentheses could be a potential u value. We'll let the u value be cosine theta. Derivative is negative sine theta. Solve for d theta. Cross multiply, we get d theta equals du over negative sine theta. We make our substitutions. The u gets plugged in for the cosine theta. D theta gets replaced with du over negative sine theta. So when we do that, we see the sine thetas will cancel out nicely, but careful, there's a negative we got to keep track of. So that -1 gets pushed out in front. We're left with u squared, which is a nice power rule. Becomes u cubed over 3. Replace the u back in terms of the original variable, which is cosine. And now we can work in those original bounds to find the definite integral. So upper bound is pi, lower bound is 0. Plug pi in for theta. Minus, then repeat the same thing, plug 0 in for theta. Again, careful with zeros. Zeros doesn't always necessarily mean it's going to just take everything out. In this case, there's going to be some leftovers. So first thing is cosine pi. Cosine pi is -1. -1 cubed is negative. Negative times negative is positive, so that ends up with 1/3. Here, we have two negatives, which becomes positive. Cosine of 0 is 1. 1 cubed is 1. So that remains a positive 1/3. 1/3 plus 1/3 is 2/3. All right, number 18. We see this is a problem where only one term in the denominator. I can move that up to the top. And if I distribute, expand, I can just treat them like separate problems. So negative x plus x will be 0. E to the 0 is 1. So we're left with integral of 1 plus e to the x. Integral of 1 plus e to the x, 1 becomes x using power rule. E to the x, antiderivative e to the x is just e to the x. And then no u substitution, so this is already in terms of the original variable. We plug in our upper and lower bound. Upper bound gets plugged in for x. We get 1 plus e to the first power. Minus, big parentheses, repeat the same process. 0 plugs in for our lower bound, gets plugged in for both variables. So 0 plus e to the 0. Again, the 0 is not going to wipe everything out. So 1 plus e minus 0 minus is 1, because the negative distributes. The 1's cancel out. We're left with just e, and that's our answer, A. Okay, last one here. This is a popular type of problem that has shown up on AP exams quite a bit, so let me go through this in detail. If the substitution of u equals square root of x plus 1 is used, then the definite integral from 0 to 3 of dx over x square root of x plus 1 is equivalent to. So we look at how this problem is set up. This is not something that we can expand, so we're going to have to go through u substitution. We'll let the u value be square root of x plus 1, because that's what the problem is telling us to do. And let's see what results out of that. Okay. We let the u value be square root of x plus 1, get it ready for chain rule, rewrite it as x plus 1 to the 1/2. Our derivative is outside's derivative, which is Bring down the 1/2, keep the parentheses, subtract 1 from the exponent, then multiply by the inside function's derivative. Clean this up a little bit. We get 1 over 2 square root of x plus 1. Cross multiply. We get dx equals 2 square root of x plus 1 du. We substitute back into our original problem. Dx gets replaced with 2 root x plus 1 du, and our u gets plugged in for square root of x plus 1. And we're able to get that to cancel out. And we have x left over. But that x is not going to go away initially, so we're going to have to go through another set of substitution here. We let the u value be square root of x plus 1. We square both sides. We get u squared equals x plus 1, and we get x equals u squared minus 1. We make that substitute back in. So now we have du over u squared minus 1. This is not something that we can easily solve, so we'll leave it in that form. The problem is only asking for us to match the answer choice. So we just have to make some adjustments with our lower and upper bound. Right now, our lower bound is in terms of x. Upper bound is also in terms of x. So we're going to push it through our expression that relates u and x together, which is u equals square root of x plus 1. Plug 0 in for x, plug 3 in for x, and let's see what our new converted values are in terms of u. So we plug 0 in for x, we get square root of 0 plus 1, which is square root of 1, which is 1. Plug 3 in for x, we get square root of 3 plus 1, which is square root of 4, which is 2. So our new lower bound is 1, our new upper bound is 2. We have a 2 out in front as well, and that matches our answer choice B.